Hi, this is Seth, and this is section 3 of Stat 111. Today we're going to talk a little bit about some more tools for asymptotics and consistency. Then we're going to talk a little bit about score, Fisher information, and KL divergence. And then we're going to finish off with a little chat about CRLB and properties of the MLE. And we're going to do some problems intermixed with that. But first we're going to talk about tools for asymptotics. So you already know a couple of important tools for asymptotics from Stat 110. The first two of which were the law of large numbers and the central limit theorem. And remember, the central limit theorem was a result about convergence and distribution, whereas the law of large numbers talked about convergence and probability and convergence and distribution. And the law of large numbers and CLT are going to be really important to kind of as building blocks for Slutsky's theorem, the continuous mapping theorem, and the delta method. But before we dive too deep into the nitty-gritty here, I want to talk a little bit about the motivation for these asymptotic tools. So say that you have some estimator, theta hat. You're trying to estimate theta, which let's just say it's the mean. And your estimator is the sample mean. And when we write down this estimator, we think about it as one thing, but it's actually like infinitely many things because it depends on n. So if n equals 1, we have one estimator. If n equals 2, we change this n up here to 2, and we have a different estimator. All the way on and on, all the way up to some arbitrary n, and then we can go on and on to infinity. And we might want to think about what happens for a specific n, but we might also want to think about what happens in a utopia world where we have infinite amounts of data. Because if we have large enough data, it might be that thinking about when we have infinite data is a good approximation for large n. And the reason that we do this is that we would always look at a specific n in an ideal world, but the math is really hard when you look at specific instances of n. And the math actually gets really easy if you assume that you have a large enough n for asymptotics to kick in. And you can show, like via simulation or lots of papers have been written on this kind of thing, that you don't actually need this n to be very large for a lot of these good asymptotic properties to kick in. So oftentimes asymptotics are a good approximation for even reasonable sizes, reasonable sample sizes. So we learn these asymptotic tools to make our lives easier and to give us good approximations. Cool. So the first of these tools is Slutsky's theorem. So Slutsky's theorem says that if you have two sequences of random variables, x1 to xn and y1 to yn, that kind of go on into infinity, and you have the property that xn converges in distribution to x, and y sub n converges in distribution to c for some constant c, then you have these three nice properties. That the sum of the y sub n's and the x sub n's goes to x plus y, that the product goes to the product of the two things that they converge to, and that the quotient goes to the quotient of the things that they converge to, provided that you're not dividing by 0. One thing to note here is that when you have yn converges in distribution to a constant, that's the same as writing yn converges in probability to a constant. If you remember from section 1, we talked about how convergence in probability and convergence in distribution are the same for a constant. And just remember, in general, convergence in probability does imply convergence in distribution, but convergence in distribution does not, in general, imply convergence in probability. Great. Now, a general biohazard is to make sure that y sub n converges to some constant. If y sub n converges to a random variable, then Slutsky's theorem does not apply, right? We do not have that the sum of the x sub n's and the y sub n's goes to the sum of the things that they converge to. And here's a counterexample. Consider x sub n equals y sub n equals x, where x is distributed normal 0, 1, and y is distributed negative x. Well, clearly x sub n goes to x because, x sub n is x. but also y sub n converges in distribution to y, since negative x has the same distribution as x, right? Since the standard normal is symmetric. However, x sub n plus y sub n is equal to 2x, and x plus y is equal to x minus x, which is 0. So we have that xn plus yn does not go to x plus y. Right? So in order for Slutsky's theorem to apply, we need to make sure that y sub n goes to a constant. Okay. The continuous mapping theorem is also another nice tool that we have at our disposal. The continuous mapping theorem says that if you have g, a continuous function, and you have either convergence in distribution or convergence in probability, then you can apply this continuous function and still have convergence in distribution or convergence in probability. This is really nice, and it basically says that for convergence, continuous functions, preserve that convergence in probability or convergence in distribution. Great. The delta method is really useful when we're dealing with sample means. So the delta method says that suppose that you have this statement, and I want you to stare at that and see if anything, it reminds you of anything. And about now you should be going, oh yeah, that looks exactly like the central limit theorem result, right? So this is the central limit theorem result, and you can check that in the book. But this is saying that if you start with some sample mean, and you want to apply some g to the sample mean, where g is a differentiable function, then we know what the asymptotic distribution of that function of the sample mean is. It's given by this complicated equation. Now, this is typically the way that you'll find it written in books. I find this version much more easy to understand. So you know that the sample mean has this asymptotic distribution for large n, right? It's centered at the true mean, and the variance is sigma squared over n, right? Okay, cool. So if you apply some function to the sample mean, then what the delta method says is that this function of the sample mean is centered around g of mu times the same variance that you had before, except there's this scaling factor, which is g prime evaluated at mu squared. Okay? And that's basically all the delta method is saying. It's saying that if you apply some function to a sample mean, then the asymptotic distribution is going to be centered around that function applied to the true mean times some scaling factor. And the variance is going to be multiplied by some scaling factor. Okay, cool. So if you ever need to find the asymptotic distribution of a function of a sample mean, go ahead and use the delta method. Great. Now, right about now, you're saying, Seth, why do I need to know all of these things? What are they useful for? And, well, they are often useful for proving consistency. So like we were talking about, we might have some, list of estimators, and we want to know how good that estimator is. And we want actually to know the specific case in which we have infinite data. If we have infinite data, then we really hope that our estimator goes to the thing we're trying to estimate, right? It would be super duper bad if when we have infinite data, our estimator is way off. Because the best case scenario is when we have infinite data. If our estimator is way off when we have infinite data, then that's a really bad estimator. Right? The bare minimum for our estimator should be that if we have infinite data, the estimator goes to the estimand in probability. And that's what consistency is saying. Consistency is saying that if you have infinite data, as n approaches infinity, then your estimator should go to the estimand, the thing that you're trying to, estimate. That's the bare minimum for your estimator. Cool. And to prove consistency, there are several approaches that you may want to consider. The first of which is showing that the MSE goes to 0 as n approaches infinity. That is one way that you could do it. Another way is to show it by the law of large numbers, or you could show it using the continuous mapping theorem if you have a function of a sample mean. And then you can also directly show it using the definition of convergence. But a lot of times in order to, show consistency, what we'll end up doing, or to even show the asymptotic distribution, like what does this estimator go to in distribution in terms of a random variable? Like what is z? We will use our tools for asymptotics. Okay, cool. This is a good place to do a problem. Okay, so now we're going to do example 1, which says using tools for asymptotics, we need to find the asymptotic distribution of the uncorrected sample variance, defined here, where the yi's are iid with mean mu and variance sigma squared. I gave a couple hints here because I think this problem is hard. It's also one of the examples in the book, but I don't think that it's worked out as fully as it could be. So it's example 3.5.6 in the book. And I'm just going to tease it out a little bit more. Great. So we start by writing square root of n, s squared minus sigma squared here. And I want to add a special 0. And the reason I want to do that is to apply the law of large numbers. So I want to apply the law of large numbers. And in order to have the law of large numbers, I need some sample mean and some true mu, right? So if I write this out in terms of sums, what I actually have here, yi minus y bar squared minus sigma squared. I have this y bar, but I don't have mu, and I want to get a mu in there. And so the way I will do that is to add and subtract 0. Is to add 0, so I subtract mu and I add mu in there. All in all, this is adding 0, so I'm allowed to do that. I square this whole quantity, subtract sigma squared. Okay, so now I'm going to expand this guy out. So this is, and I'm going to do this in such a way that this guy is a, this guy is b, and I'm going to write a squared plus b squared plus 2 times a times b. So yi minus mu squared plus some mu minus y bar squared plus 2 times sum of yi minus mu, mu minus y bar minus sigma squared. Great. Okay. Now it looks like I've just made it a lot harder for myself. However, we know by the law of large numbers that y bar converges in probability to mu, which implies that mu minus y bar converges in probability to 0 by the law of large numbers. And by the continuous mapping theorem, since f of x equals x squared is continuous, I know that mu minus y bar squared also converges in probability to 0. And so what that tells me is that this term, since it has a mu minus y bar, that this thing converges in probability to 0, and that this thing converges in probability to 0. So asymptotically, neither of these things matter. So I can rewrite this as square root of n, 1 over n, sum yi minus mu squared minus sigma squared. Okay, and now I want to use this hint about this special central limit theorem. So I can actually just rewrite this. If I wanted to rewrite this hint, if I was to standardize, or like unstandardize this random variable, I would, standardize. I would subtract the mean, so you'd subtract sigma squared, and this would go to 0. And then to get this n out, you'd have to pull it out in front as a square root n. So that's really all that that this step does, the one that I'm about to write down. But what I can then say is that this converges in distribution to normal 0 variance of y1 minus mu squared. And that's just by using this little tidbit of information that I have here and rearranging stuff. So this gives the full asymptotic distribution of the uncorrected sample variance, and that's really nice. Hi, in this section we're going to talk about the score function, Fisher information, and KL divergence. So what is the score function? The score function is actually something that you've been learning about for the last couple weeks. It's just the first derivative of the log likelihood. So congrats, you don't have to learn anything groundbreaking or new in this section. You've actually been setting the score function equal to 0 and solving to get the maximum likelihood estimated. Now note that you could put anything into this theta argument of the score function. But what we're going to be interested in for the most part is the score function evaluated at the true parameter. And when we say true parameter, we mean, the ground truth, the way that the data were actually generated. Okay, so if we are at the true parameter, then we have a couple nice identities about the score function, namely that the expectation of the score is equal to 0, and that the variance of the score is equal to the negative expectation of the first derivative of the score, if we're at the true parameter. Now note that when we're taking these expectations and variances, the true parameter is fixed and y is random. And the regularity conditions are here, but you really don't need to know all that much about them. The one that I do want to flag for you is that if the support of y depends on theta, then weird things can happen. So for example, if y is uniform 0 theta, that's really bad since the support of y depends on theta. Then you really don't want to trust the maximum likelihood estimate, or and some of these results break down. Equation 2 is called information equality, and that's because of a result that is derived on page 115 of the Stat 111 book in chapter 4. Since it's called information inequality, you're like, well, what information are we talking about? And we're talking about the Fisher information, and that's because it is equal to the Fisher information of the vector y evaluated at the true parameter, which is exactly what point 3.2 says, that the Fisher information is just equal to that second equation up there. Great. Now sometimes from a notational perspective, we suppress the star and just write y, theta star as I of theta, and that's really written as the Fisher information of theta. Now what does the Fisher information tell us? Essentially what it tells us is how much information does a random variable y give us about our parameter theta. So a high Fisher information indicates that the likelihood has a pointy peak. So just on this graph, these are potential values of theta, and this is, the likelihood of theta. A high Fisher information says that at the true parameter, we have a really pointy peak, which means that we can rule out values of theta that might be relatively close to the true value, but are not the true value. So like the likelihood is so small here relative to at the peak that we can probably say that this is not the true parameter. However, if the likelihood is not pointy, if it's something like this, then it's hard for us to rule out this value since it's so close to the likelihood at the peak. So this is low information. So we would prefer to have high information because that peak is pointier, and then we can rule out more values of theta that are close by. So we're hoping for high Fisher information. Great. Now in problems, oftentimes you'll be asked to find the Fisher information. It's important to know whether you need to find the Fisher information of one observation or of all of the observations. So make sure to read the problem carefully to know what the question is asking before doing lots of calculations. It's a mistake that I made when I was taking the course. And something that's very, very important is that in the IID case, the Fisher information for a vector of data is equal to n times the Fisher information of just one observation. This is only in the IID case. Fisher information is also useful for the CRLB, which is the Cramér-Rao lower bound, in the asymptotic distribution of the MLE. We'll talk about this more later. If you reparameterize the parameter, then the Fisher information changes, and it changes according to this rule. So say that we found the Fisher information in terms of theta, and then we want to find the Fisher information in terms of tau, where tau is equal to g of theta. Then we just use this formula. The Fisher information of tau is equal to the Fisher information of theta divided by g prime of theta squared. Great. Okay, so we're going to do example 2, 1 through 3, or A through C, as an exercise in the score and the Fisher information. So first let's find the score of theta and verify that its expectation at the true parameter is equal to 0. Now we have our data, x1 through xn, which are IID, normal, 0, theta, where the variance is unknown. So to get the score, we want to get the first derivative log likelihood. So let's start with the likelihood of theta, which is a product from 1 through n, since we have IID data, of a normal PDF, which I'm just going to write like this. And you can verify that that is indeed the normal PDF. I'm going to write this as theta to the negative n over 2 product I equals 1 to n of exp x sub I squared negative, over 2 theta. Cool. Okay, so then we want to write down the log likelihood, which is just taking the log of this. So if I take the log, I get negative n over 2 log theta minus sum of xi squared over 2 theta. I'm actually going to pull this 2 theta out since it's a constant. Okay, cool. And then I'm just going to take the first derivative of the likelihood to get the score function. So it's worth noting that this is the score. And over 2 times theta. Then here, because of the chain rule, this turns into a positive, and it's 1 over theta squared, xi squared. Perfect. Now, what I want to do is I want to evaluate the expectation of the score at the true parameter. Okay, so when we plug in the true parameter, what we're assuming is that each of the xi's are really distributed normal, 0, theta star. And we want to take an expectation with respect to x. Cool. So let's just write out an expectation of the score. And what we're going to do is we're just going to copy down this score function. And everywhere we have a theta, we're going to write theta star. And everywhere we write an x, we're going to make sure that we have this big X. Okay? But now, since we're taking this as a constant, we can pull it out from linearity. We're going to apply linearity again on this sum, e of xi squared. But we know that xi is distributed like normal, 0, theta star. And since the mean is 0, we know that this second moment is just equal to theta star. And so what we get is minus n over 2 theta star plus, since we have a sum from I equals 1 to n, we actually have n theta star squared. Sorry, I dropped a squared here. Theta star. These theta stars cancel out, and that is equal to 0. And that is part A. So for part B, we want to verify information inequality. So let's start with the variance of the score. We've already got the score. And we're also taking this variance with respect to the random data. Remember that we're assuming that this is the true data generating process and that our score function is here. So in order to take the variance of this, what we're going to do is we're going to, again, replace this with big X and put stars on everything in here. Okay. Note that this is a constant, and additive constants don't matter when we're getting variance, and multiplicative constants come out squared. So the first thing I'm going to write down is that this is equal to 1 over 4 theta star to the 4th times the sum of the variance of xi squared. And the reason I can take this variance inside is because each of the xi's are iid. Cool. And then I'm going to use the hint, which says that the 4th moment of a normal with mean 0 and variance sigma squared is 3 sigma to the 4th, because the variance of xi squared is equal to the 4th moment minus the 2nd moment squared, just by definition of variance. So this is 3 theta star squared minus theta star squared, which is equal to 2 theta star. Just this variance guy here. And so, since I'm summing from I equals 1 to n, I have n of those. This is actually equal to n over, or n theta star squared for theta star to the 4th, which is n over 2 theta star. Sorry, yeah, I forgot a 2 here. But yeah, n over 2 theta star squared. Cool. Now I need to take a look at the expectation of the score at the first derivative of the score, right? So I want to show that this is equal to negative the variance of s theta star x. So the first thing I need to do is get the first derivative of the score. And, well, let's use this version of the score then. If this is the score, well, I need the first derivative of the score, so I need to take another derivative here. So, derivative of this is n over 2 theta squared plus, it's actually going to be minus, because of the chain rule, 1 over theta cubed, the sum of the xi's. And this is equal to s prime theta. Then I want to take the expectation of this. So n over 2 theta star squared minus 1 over theta star cubed, sum from xi squared. Cool. This is a constant, linearity there. So I've got n over 2 theta star squared minus 1 over theta star cubed, sum expectation xi squared. This is theta star by the same argument that I made earlier. Since we've got a sum, this becomes n theta star. So this is n over 2 theta star squared minus n over theta star squared, which is equal to negative n over 2 theta star squared, which is, in fact, the negation of the variance that we found earlier. So we verified information inequality. Cool. C was telling us to find Fisher information of theta such that the Fisher information of tau is a constant. So first of all, what's the Fisher information of theta? Well, it's just the variance of the score, which we've already found. So it's n over 2 sigma star, or theta star squared. And now I want to find a variance stabilizing transformation such that theta tau, which is equal by the parameter transformation rules to this, is equal to a constant. Okay. So I'm trying to find something 2 theta star squared over g prime of theta squared is equal to a constant. Well, the way I make this equal to a constant is if the theta stars cancel out, right? So the way that I do that is I let g of theta equal to log of theta, because then g prime of theta is equal to 1 over theta, and g prime of theta squared is equal to 1 over theta squared. So therefore, the information of tau is 1 over theta star squared, or I suppose, 1 over theta star squared. Remember, sometimes we suppress the stars. I'm just writing out the stars now. These will cancel. This will equal n over 2, where n is known. It does not depend on tau, no matter what tau we have. The Fisher information of tau will be constant, and so the transformation that we want is g of theta is equal to log of theta. So let's talk a little bit about KL divergence now. So the KL divergence is one way of telling the difference between two distributions f and g. Rigorously, it's the expectation of the log of the quotient of their PDFs, but I like to think of it more as the expectation of the log of density f minus the log of the density g. Now, often this is referred to as, a difference between the densities f and g, but note that for the more mathematically inclined among you, it is not technically a distance. In the very metric sense, it does not satisfy the triangle inequality, and you can read more about that on your own time. What we are mostly interested in is the fact that this looks a lot like the log likelihood of f, and this looks a lot like the log likelihood of g. So often what we'll do is we'll have two candidate parameters, theta 1 and theta 2, that may have plausibly generated the data at hand, and we want to see which one is more plausible. And the KL divergence, tells us how different those two data generating distributions are by taking an expectation over all of the possible, all of the data with respect to one of the potential distributions. If we have the true value, if one of these thetas is the true value, then what we're doing is we're saying how different is theta 2 from the true value. How different is the whole distribution of theta 2, the whole data generating distribution, if theta 2 was the true parameter, versus what the true parameter actually is. So again, we can write this version as the expectation of the log likelihood evaluated at the true parameter minus the log likelihood at some other parameter. Now notice that the likelihood is maximized at the true parameter, which means that this is always going to be a positive quantity. Cool. Another interesting fact about the KL divergence is that the second derivative of the KL divergence is the Fisher information. So the curvature of the KL divergence at theta star is equal to the Fisher information. Overall, the KL divergence is not the most important topic in 111, but it will be important for you if you go on to study more information theory. And so we bring it up. If you have more questions about it, I would be happy to answer them over email or in office hours. The CRLB and the properties of the MLE that we're going to talk about are much more important in the grand scheme of Stat 111. So yeah, this is something that is very important. So the CRLB is a lower bound on the variance of unbiased estimators. So under regularity conditions, any estimator that is unbiased for theta has a lower bound of the variance of that estimator as 1 over the Fisher information of all of the data. So this is saying that, like, in the best case scenario for an unbiased estimator, the variance is at least the Cramer-Rao lower bound. Cool. Since we've also assumed unbiasedness in this case, this is a lower bound also on the mean squared error for unbiased estimators. It's also worth noting that the MLE achieves the CRLB asymptotically. However, the MLE is not necessarily the only estimator that achieves the CRLB. There's also a more general form of the CRLB, which is given here for any estimator. It doesn't have to be unbiased. Great. Okay. Now finally, let's talk about some properties of the MLE. 1, the MLE is consistent, which is really nice. So if we have infinite data, then we know that the MLE is going to go to our estimand. Another nice thing is that asymptotically, the MLE is normal. Under regularity conditions, the MLE minus the true parameter times square root n converges in distribution to 1 over the Fisher information of a single observation. This is really, really, really nice. Okay. So for the asymptotic distribution of the MLE, let's do a practice problem. Okay, to get some practice with this, let's do parts D and E of example 2. So first we want to find the MLE for theta, and if you'll recall from the last part of the problem, we already found the score. So what we want to do is set the score equal to 0 and solve. So this gives us, if we just rearrange terms here, and we get this, sum from xi squared. What we can do is we can cancel this 2, cancel this theta, and then solve for theta. So we get theta hat is equal to the sum of the xi squared over n. And this is our MLE. Now we want to show its consistency. Well, what you'll notice is that this is the second sample moment. And we know by the law of large numbers that the second sample moment converges in distribution to the true sample moment. But since we know that x1 is distributed normal 0 theta, the second moment is just theta. Therefore, we know that the MLE converges in probability to theta, which shows consistency. Finally, we can take a look at the asymptotic distribution of the MLE just by following our formula here. So if we literally just, plug and chug, we have that theta hat MLE minus theta star with a square root n up front, converges in distribution to normal 0 times 1 over the Fisher information of one observation. And we found in part C of the previous problem that the Fisher information of n observations is given by this equation. And since we have IID data, that indicates that the Fisher information of one observation is 1 over 2 theta star squared. And so 1 over the Fisher information is 2 theta star squared. This begs the question, what is the CRLB? And the CRLB for all unbiased estimators is 1 over the Fisher information of n observations. And so what we have is 1 over n 2 theta star squared, or 2 theta star squared over n.